So thanks, Oliver. In my presentation, I'd like to I'd like to present you some recent results about a new type of GLONASS spacecraft, which is called GLONASS K1+. And I'd like to start with an overview about the different generations of GLONASS spacecraft. So basically we have 4 different types, and some of them even have some subtypes. All of them transmit L1 and L2 FDMA signals, frequency division multiple access. So this is a unique feature for the GLONASS constellation, where each individual satellite is identified by its frequency. So the very first generation of satellites, does not work. The very first generation is not active anymore, so this was then preceded by the modernized spacecraft, and we have in particular an updated version which is called M+. Okay, here it comes. So M+ is the first generation of spacecraft that introduces an L3 CDMA signal. So CDMA, code division multiple access, like all the other GNSS use, where the code signal is unique and identifies the spacecraft. So M+ satellites transmitted the signal via a dedicated antenna, and the same was also true for the very first K1 spacecraft labeled K1A. So here also a dedicated antenna was used for this L3 CDMA signal. Then the next generation, the K1B, had the same set of signals, but only one antenna. And in this talk I will focus on K1+, which adds the L2 CDMA signal again from a dedicated antenna. Since August last year, we also have the first K2 satellite in orbit, and this adds also the L1 CDMA signal. And you can see here dedicated antennas for the FDMA and for the CDMA antennas. So we currently have one K1+ satellite in orbit. This is SVN R807, which was launched in October 22. It started in November signal transmission. It is regularly tracked by the receivers of the IGS, but one special thing is not tracked by these receivers, and this is the L2 CDMA signal. So currently none of the IGS receivers supports tracking of this signal due to firmware issues. And one special thing is, I will come back to this later, is the suspected use of a new type of clock, so maybe a hydrogen laser is flown on this type of satellite. On the right-hand side, you can see here the character-noise density ratio of different signals obtained with a Javad TRE-3S receiver at our institute of Oberpfaffenhofen. So this has a prototype firmware which is able to track the L2 CDMA signal, and the averages of 8-day data arcs are shown. So this is the ground repeat period of GLONASS. So if we have a look at the legacy signals, so we have here the green and the orange curve as well as the blue have basically the same shape. They are shifted somehow, but these are all transmitted from the same antenna, from the central antenna. And you see the L2 CDMA signal, so the red one, it has a completely different shape. So it has much higher gain at high elevations, indicating that this is really coming from a different antenna. Here is shown a spectrum of the L2 frequency band as obtained with our 30-meter dish antenna in Weilheim. And you can first see here a prominent peak, a sharp peak, which is related to the legacy FDMA signal for frequency channel number -5. And then a little bit shifted is the central peak of the L2 CDMA signal. So this central peak is composed of 2 components. The one is the channel for service information, and the other one is the open service signal. Furthermore, we have a secure service. This is then shows up as these 2 peaks shifted away from the center frequency. So this is due to the binary offset carrier modulation, which shifts away the power from the center frequency by ±, 5 megahertz. And you see some side lobes of this secure service. So we have now observations on different frequencies, and we can use these to form triple carrier combinations. So here we form a linear combination that eliminates the geometry and the ionosphere from the L1 and L2 FDMA signals, as well as the L3 CDMA signals, so all signals that are transmitted from the main antenna. And what we would expect is basically noise, maybe some multipass, but what we see for this GLONASS K1 Plus is something completely different. We see a periodic variation with a peak-to-peak amplitude for here in January 2024 of about 20 centimeters and a period, in this case, of about 2 hours. This is not fixed, so the period varies, and the period is shown in this plot. So on the x-axis you see the day of the year, and on the y-axis the time of the day, and color-coded is the magnitude of this triple carrier combination. And you see that we have periods with very high variations, then we have with almost no variations. In white are shown transmission outages, so changes are usually accompanied by these transmission outages. So let's have a look at the spectral domain. What happens, which periods do we see? So the lower plot is simply a zoom of the upper plot, and we have periods with very high frequency variations. So this corresponds to about 15 minutes per day, and some other periods with about 2 hours, and also some very low frequency variations. So what could be the explanation for these variations? One is a clock hardware failure, that something is simply wrong with the hardware of the clock, and another possibility is a crosstalk of oscillators with slightly different frequencies, and these cause range variations. The equation is shown here, and the cross-coupling factor that we obtained here, which dampens the amplitude, is about 0.02 for what you have seen in the previous slide. So nevertheless, let's have a look at the clock performance of the satellite. Here is the one-way carrier phase analysis used only for very short period clock variations. So here a GNSS receiver is connected to a highly stable clock, a hydrogen maser. So we can assume that this can be simply modeled by a second-order polynomial. The second-order polynomial also removes effects of the ionosphere and the troposphere, and then we end up with basically the signal of the clock. And the L deviation of all GLONASS satellites are shown here on the left-hand side. So you see the thick green line is the one of the GLONASS K1 Plus. And this outperforms at longer integration times all of the other GLONASS clocks, indicating that this might be a new type of clock. We can also have a look at time series obtained from this one-way carrier phase analysis. This is shown here for the L1 and L2 FDMA signals, which show a good consistency. So the pink and the black curve you cannot always distinguish, so a good consistency, but for the L3 CDMA signal we see as well a slight phase shift and an increased amplitude. And these differences then end up in the variations of the triple carrier combination that we have seen before. So let's have a look at the antenna configurations. So we have one central antenna array, which is composed of these 12 helical elements, so similar to GPS, and we have a dedicated single antenna element for the L2 CDMA signal. So what is here called in a simplified way baseline is not the exact geometric distance between these two phase centers, but it's basically the triple frequency combination of the antenna and frequency-specific phase center offsets. And we can now use again a triple carrier combination now of different signals of L1, L2 FDMA and the L2 CDMA signal. to obtain the baseline. So the observation equation is shown here. We have here our triangle carrier observations. We have the geometry, something about the attitude. We estimate the baseline, ambiguities. We model the phase windup, and we have some remaining errors. And we do this on a daily basis, and the results are shown here. This is obtained from only 2 receivers. To our receiver in Oberpfaffenhofen, we have another one in Sydney that is also able to track the L2 CDMA signal. And with these 2 receivers, we estimate the baseline on a daily basis, and these are the blue dots shown here. So in X direction, we have a scatter on the roughly 1 centimeter level. In Y direction is even smaller. And the orange cross indicates the mean value of our estimates from about 6 weeks of data. And it's interesting to note that this agrees on the 1 to 2 centimeter level with the this red cross here, and the red cross stands for the first K1 satellite, which had a dedicated antenna for the L3 CDMA signal. So it's, I think, reasonable to assume that at least a similar, if not the same, design of this additional antenna is used for the K1 Plus satellite that was previously also used on the K1A satellite. Okay, let me come to the conclusions and some questions. Some conclusions with question marks. So the GLONASS K1 Plus satellite has some new features. It is the first satellite transmitting the L2 CDMA signal. It has a dedicated antenna for this signal. It might have a new type of clock. This is not confirmed, but the performance points at this. We have identified pronounced periodic variations. They have period between a few days and down to 15 minutes. The reasons are unknown, so it could be either hardware failure or crosstalk of 2 oscillators. And the final question, we do not know if this is a single prototype satellite or if future K1 satellites will all have these properties, so we have to wait until the next launch of this type of satellite to answer this question. Thanks for your attention.